Hi, I'm Charles. If you have been following my channel, you must know that I'm a bit obsessed with lenses. So I think it's about time I should discuss the chemical and a bit of the physical properties of optical glass itself. Because as we shall see, it has a great impact on the visual properties of the image that is obtained from the whole optical pathway. Glass, in its simplest form, is a mixture of sand, lime, and soda. It is melted at a very high temperature of about 1500 Celsius, and then it's slowly cooled down. How slowly? Usually the cooling process of glass lasts about 2 to 3 weeks. It is done to maintain the glass in a supercooled liquid phase. Glass is not strict solid, because when sand solidifies, it becomes crystalline, which means it is not transparent to light. It reflects most of the light hitting it. So it needs to be maintained in its liquid phase. So it needs to be supercooled to allow for rearrangements of electrons along the magnetic field created by light. The two main characteristics of optical glass are refraction and dispersion. Refraction occurs when the light passes from air or vacuum to a liquid. The electrons inside the material interfere with the flow of light photons, which are electrically charged, and the speed of those light photons is actually slowed down. Accordingly, the angle of flow changes inside the material. Now, the denser the glass, by dense I mean the density of electrons inside the glass, the larger the change in the angle of light. The refraction is affected by the chemical composition of the glass. By replacing some of the silicon oxide in the glass material with other minerals, you can change the refraction index, so the amount of change in the angle of light entering the glass. You can either increase the refraction or decrease it. Increasing the diffraction is done by adding oxides of heavier metals, such as mainly lead or lanthanum, to the sand. Decreasing the refraction index is done by replacing some of the sand with lighter metals or oxides of lighter metals, such as potassium oxide, etc. The second property of glass, which is related to refraction, is dispersion. You see, not all light changes its angle to an equal degree. High energy photons, like the blue part of the light spectrum, still flow at a greater speed through the glass than low energy photons, such as yellow or red ones. So when the light beam passes through the glass, it separates a bit, and we get a rainbow effect, where some of the light is focused closer to the glass or glass element than other parts of the spectrum. This causes what is known as axial chromatic aberration. Longitudinal chromatic aberration occurs when different parts of the light spectrum focus on the same plane, but at different heights on the focal axis. And this is a phenomenon that creates some color fringing, mainly at the edges of the resulting image. As I said before, light dispersion or chromatic aberration is related to refraction. The change in the angle of light is of course proportional to the change in the angles of individual parts of the spectrum. The typical refraction index and Abbe number, which is the opposite or negative of the propensity for light dispersion, are presented on the shot chart, which spreads out a large amount of optical glass types. And you can see where each glass types, each of the glass types falls on this range. The vertical blue line in the chart represents the Abbe number of the eye. As you can see, an Abbe number of 45 means that we are not very sensitive to chromatic aberration in our natural vision. There are many types of optical glass that have a higher Abbe number than our eye's Abbe number, which means those glass allow less chromatic aberration than we can see with our naked eye. But that changes when we consider enlarging optics, because the more you enlarge the image or the scene, the more fringing becomes apparent. This happens either in telephoto or microscopic applications, or when we enlarge the view of photographs on our computer screens. During the film days, chromatic aberration was less of a problem. Most of us looked at images after they were printed on paper, and fringing was not very evident because our eyesight does not allow us to really see it. But when you pixel peep or really enlarge the image, these artifacts become more apparent. And since lens manufacturers have to compete with each other, there has been a tendency to reduce chromatic aberration by using higher and higher Aber number materials that are less sensitive to dispersion. Now, the problem is that dispersion is related to refraction. Now, we have to remember that the function of lenses is basically bending light, focusing it or dispersing it. The thing is that high refraction index glass is much more efficient in bending light than low dispersion glass. So the curvature of those low dispersion glass types has to be stronger in order to achieve the same effect of a low curvature or weak high refractive index glass element. And those strong curvatures dictate that low dispersion elements are much thicker and require more space inside the lens barrel. In practice, the resulting consequence was the production of some really large, long and wide lenses that were widely abundant about 10 years ago. But the transformation of the market from DSLRs, which were large cameras, to mirrorless that enables using smaller form factors of cameras, requires smaller lenses. On the other hand, the rigor of reviewers or users of optical lenses, especially with higher and higher resolving sensors. Now, to achieve very sharp, clinically sharp image, you really need to use a lot of low dispersion glass in the lens, because it is less resistant to light. It tends to avoid those visible artifacts of not only chromatic aberration but also reflection and internal reflection. So the more resolving power the sensors and the cameras have, the more you have to really use such glass types. This is not only limited to telephoto lenses. Every lens introduced in the past 5 to 10 years contains at least one low dispersion or ED element. There are some exceptions, mainly in lenses made for rangefinders that have to be maintained small to avoid viewfinder blockage. But in mirrorless systems, almost all the lenses that are being introduced have a high resolving power, which is mainly due to the abundance of low dispersion glass. Now, low dispersion glass, as I said, has to be more strongly curved in order to achieve its optical function of bending the light, are more sensitive to another type of aberration, which is spherical aberration. This artifact results from different focal points for light that comes from the center of the glass element and from its periphery. So typically that can be corrected by using more aspherical elements in the lens. However, all those elements that correct each other add up, and they make really large lenses. High refractive index glass has its advantages too. Besides their lower requirement for curvature, which means the glass elements can be thinner because of their high efficiency in bending light, they make images that are more cohesive. That is because of the higher sensitivity of these lenses to reflection. Of course, there is external reflection, light rays hitting the glass element at an angle may bounce back, and those glass elements are usually heavily coated in anti-reflected materials to minimize those types of reflections. But those glass types also suffer from internal reflections, where light rays bounce forth and back inside the glass itself, which creates lateral movement of light inside the lens element, and that is apparent in some glow that is visible at higher apertures in lenses containing a lot of high refractive index glass. Of course, glow, that glow is what gives some of those lenses character. In addition to that, those glass elements create what I like to call micro gradation, where the tonal transitions around the edges are more gradual. You do get a thin transition zone around the edges that is created by chromatic aberration, of course, but also by this lateral movement of light inside the glass. It has a positive impact on the rendition of depth in the photographs we see. Curvatures appear more natural to our eyes because the upper number of those glass types are closer to the upper number of our eyes. The appearance of curvature is a cue for our brains to interpret the volume or weight of objects in the scene, and for the true-to-life perception. Too much use of high refractive index glass in a lens will have the effect of creating a low contrast image with a very glowy, dreamy nature and quite a beefy or meaty appearance of the bokeh. Those images are really not very sharp because there is a lot of chromatic aberration going on, which actually has an effect of the overall color of the image. Those lenses were made decades ago when color photography was not available yet. Too much use of low dispersion or low refractive index glass in a lens will create very sharp but also very flat image, which is okay if you treat the pixels as a population, or if you run statistics over them in scientific applications, or when you want to portray a flat object, such as a painting. But for three-dimensional scenes, including landscapes and even architecture, you do want some depth in your photo, or at least the perception of depth by the viewer. You really need to mix glass of different refractive indices. I would say that a good proportion of high refractive index in a lens is around 10 to 20, maybe 30%. Depends on the other types of glass used in a lens. More than that will create a low sharpness, low contrast image. That is easy to correct, but straight out of camera it just doesn't look right. According to my analysis and experience, you should really look at lenses with less than 10% low dispersion glass. Now, there are different types of low dispersion materials. Manufacturers used to make lenses with calcium fluoride, which is a type of crystal that was used exclusively in some lens elements. That material has an Abbe number of 95, which is, it allows almost no light dispersion. But it is difficult to work with because it's fragile and the grinding leaves some abrasions on the glass surface. Anyway, it is also sensitive to temperature. It extends at high temperatures, and this is why telephoto lenses containing calcium fluoride elements were painted white to avoid excess heating. Calcium fluoride was later replaced by other materials that are easier to work with. Some of those materials are not even glass. They are made from molded polymers or plastics. Traditional manufacturers such as Leica, Falkland and Zeiss do not use extreme low dispersion glass. They rather use what they call partial dispersion glass, which is actually a type of glass that contains a lot of potassium oxide, which is a very low density glass, but it has a relatively low Abbe number of around 70, which does allow a little bit of dispersion or chromatic aberration to occur. To sum it up, you do need a little bit of high refractive index glass in the lens. This glass is able to kick back a little bit of the light that hits it, and thus, to put it crudely, the images kick back a little bit too. So they have this rendition of depth and some 3D. People shot with that, with such lenses, look alive. The the scenes look more three-dimensional and true to life. Identifying such lenses is done by looking at the structural diagram and assessing the amount of ED or low dispersion glass. Looking especially for glass types such as FLD or SLD that are very high Abbe number and which create a flat image. Alternatively, you can look at the lenses themselves, lenses that have high refraction elements in them will have a white shimmer when you tilt them a little bit towards the light, such as this Falkland 58mm f1.4. Now I must commend Nikon for making a line of more three-dimensional lenses that do not contain any ED glass, which is the f1.4 line. The 40mm f2 is another lens that has those properties. It's a very simple lens, but it does render the scene in a three-dimensional manner. Other manufacturers sadly do not produce such lenses. They keep competing for the more and more resolving power, and the lenses they keep introducing are very resistant to chromatic aberration, but also rather flat. That includes third-party manufacturers such as Tamron and Sigma. Some of the Chinese manufacturers do try to produce lenses with a little bit more character, but so far all the autofocusing lenses produced by third-party Chinese manufacturers such as Viltrox, TT Artisan, and etc. Do not have a 3D rendition. I know that I'm generalizing here, but I would really like to encourage manufacturers to produce nice lenses that are fitted for three-dimensional scenes. Now, who really cares about corner sharpness when you photograph people or a street scene or anything really? Few of us look at the corners, and even the lens filming me now, the Nikon 35mm f1.4, which is a nice poppy lens, has a good rendition in the corners. It's the unsharpness is almost invisible to the naked eye. You need to really pixel peep to observe any problems with the images. Right, that will be all for today. Thank you for watching.